Morning, class. My name is Kellen Underwood. Today, Team 1 will be giving you a presentation on heat dissipation technologies and techniques. Again, my name is Kellen Underwood. I am document prep for Team 1.
Hello, my name is Ron Cathy, and I am the project manager.
Mason Pike, webmaster.
Killian Davis, lab coordinator.
Mike Robello, presentation prep.
Here's an overview of what we'll be going over today. I'll be giving you a quick introduction. These are the cooling techniques we'll be covering today in this lecture. Heat sinks and air cooling will be given by Cerrone. This is the use of the heat capacity of metal with a combination of fans to create airflow to achieve a cooling. Next, Mason will be giving water cooling, which is the use of heat capacity of and specific heat of water to achieve cooling. Next, liquid cooling will be given by Killian, which is the achieving cooling through induced phase changes, followed by Peltier cooling, which will be given by Mike, which is the achieving cooling through the use of semiconductors, metals, and ceramic plates. I'll be giving a quick conclusion, and then I'll be taking questions. So quick introduction, heat dissipation technology is utilized in the cooling of heat generated by electronic systems. This is to prevent failure of the system, increase efficiency of the system, and increase reliability of the system. This is achieved through two techniques, active cooling and passive cooling. Active cooling is generally the use of power to achieve the cooling solution, whereas passive cooling is not using power to achieve the cooling solution. We're going with thermal design power. It's also referred to as TDP. This is used to define the max heat dissipation for a cooling solution that can be effectively removed from an electronic heat source. Manufacturers give this as a maximum thermal dissipation load based on stock frequency of a microprocessor or microcontroller at a heavy computational load. The heat generated by an electronic source, remember, is in the energy form of power, which is given by units watts. And right here is the equation that TDP is calculated by, which is capacitance, voltage squared, and frequency. Next, I'll be giving it to Cerrone here to cover heat sinks and air cooling.
Good morning again, class. My name is Cerrone, and I'm going to be going over heat sinks and air cooling. So the first technique of heat sinks, I'm going to be talking about the passive design. With the passive design, the orientation is very important, and that's because the heat sink has to have a physical contact with the heat source in order for the conducting of heat to take place. Also, the whole idea, the design behind the heat sink is the fact of increasing the surface area. When you increase the surface area and you do a metal contact with the heat source, you're going to be able to conduct the heat through that metal more efficiently or more effectively. Also, the heat sinks, as you can see in figure 1, all of them have a solid base with fins coming out. So the orientation of figure 1 is how you would actually set the heat sink onto a heat source. The solid bases are usually made of some type of metal, aluminum, copper, and they're usually coated with nickel for corrosion purposes with contact between different metals over time. Some of the different heat exchange techniques is bonding and or using paste. Like I said before, you have to make a physical contact. In the cases where you can't physically put the heat sink on the heat source, you're going to use some type of paste or bond to make that thermal conductivity contact. And then if you can make the physical contact, there's a technique called lapping, where you use a fine grit sandpaper to rough up the surface a bit in order to make a more overall contact with the heat source. The next technique is active cooling. So what this idea is, active cooling is used when your heat source generates a whole bunch of heat to the point where your heat sink is not able to actually conduct it at a rate that's efficient for the use of that electronic device. So you attach a fan to the heat sink, and essentially the fan sucks the heat away from the heat source at a faster rate in order for you to be able to cool that, let's say, microprocessor. Some of the specifications of the fan, they're all 12-volt DC fans, and they're rated with RPMs. The more current you put through the fan, the more RPMs you'll have. So if you need a higher airflow rate or CFMs, that goes to bring on higher decibels, so it's going to be a louder fan. If you can use a bigger or a greater diameter fan that will generate the same amount of airflow but have less dB, so it'll be quieter. So some of the design factors when you want to pick out a heat sink for your own personal applications, you got to take into account the thermal resistance, which is given in degrees per watt. And they're usually low thermal resistance for big devices and higher thermal resistance for smaller devices. You want to take into account the materials used: aluminum, copper, graphite, and diamond. Copper has a bigger thermal conductivity than aluminum, graphite more than copper, and diamond is overall. The fin efficiency, you have to look at the different types of fins. There's in the different types of geometry. You have the ones you've seen in figures 1 and 2. You also have circular fins. Those are more efficient to the sense of having in the passive type of design. If you have about an airflow of 1 meter per second, the circular type fins are more efficient than all the other types of fins. Do you need a passive or active type design? Direct contact versus indirect. Again, if you need indirect, you need some type of paste or bond to put it between the heat sink and the heat source. And also there is the surface area of the contact base. What type of geometry do you need for that contact? So for the physical contact, we have what we call TIMs. It's the thermal interface materials. And there's 3 parameters that you need to take into account when picking your base or bond. It's the interface gap with which the TIM must fill, the contact pressure, and the electric resistivity of the TIM. In this next slide, there's going to be a table where you can look up on the web. So say, for example, for my own personal application, I had a 0.03 millimeter gap, so I would use the thermal grease epoxy phase change. My pressure that the chip could only withstand, let's say 100 kilopascals. So I use the thermal grease epoxy polymide, and then I go down here for the overall, and these are the ratings between the different types of base, thermal base, epoxy phase, and so forth, so forth. So the applications for heat sinks that you would take in consideration for any type of design for cooling would be microprocessors, computers, games, or cell phones. And they're big with thermal management and power supplies, amplifiers, power circuitry, and telecommunication devices. And some of the pros of the passive heat sink is that they are highly efficient in heat dissipation. They can be found in any size and any geometry, and they're pretty much limitless in their application. The cons is that they're bulky. As far as computers are concerned, when you have to actually put heat sinks on the microprocessor or any other devices in there, you have to design around it, which causes more material, more casing, and it could be a cost up. And then there's also limits. Heat sinks can only be used in environments where the ambient air temperature is less than the heat being generated, so that there could be some type of average air between the actual heat source and the ambient air, and that's where you'll get your average temperature. And now I'll pass it on to Mason, who's going to talk about water cooling.
Thanks, Saron. Once again, I'm Mason, and I'll be talking about water cooling. First of all, these are the general components that you're going to want to have for any type of water cooling system. You're going to need radiators, tubing, a pump, reservoir, fans are optional. You can have passive radiators, so essentially you won't need active cooling, but you will still need to have it powered by a pump. And then last but not least is the water blocks. Water blocks are the actual way in which the heat is exchanged from the microprocessor unit into the water cooling system. These are specific to the type of microprocessor you're going to be using. So most current processors have a socket such as 2011 with Intel or 1155, AMD has their AM3, and they'll have specific bolt patterns that a water block has to use. Additionally, GPUs, graphics processing units, have a specific water block as well for their architecture that they're going to be using. One of the main reasons to use a water cooling system is that it can cool more efficiently than, or effectively than standard heat sinks. It also allows you to use multiple water blocks in a water loop to cool multiple components with only one radiator. The radiator still works the same way as the heat sinks. Basically, you're going to be increasing the surface area in which you're allowed to dissipate heat through metal. Next slide. So some of the strengths are the cooling capability and performance of these versus the standard heat sinks. Some of the weaknesses are that over time you can get a buildup of scale and biological materials from the water. To prevent this, you either need to add additives and regularly clean your systems and basically purge and start over. Also, water can cause degradation of the actual water blocks. So when the water block sits in between your heat source and the water that flows across the other side, they'll slowly start to degrade the metal and create metal particles in your system, which can be bad for your pump over time. So once again, you need to essentially clean out your reservoir. And one thing I want to lead in with is that the water cooling systems are very versatile. They allow you to use, which we'll be talking about here, liquid cooling processes. You can actually apply the radiator directly to the evaporator coils to cool the entire system below ambient for improved performance. Now the problem with that is you'll need to insulate the entire system. If you want more performance directly at the chip level, you can use Peltier, which Mike will talk about in a minute, and that will allow you to essentially have increased temperature differential between the chip you're cooling, and then that will then be pushed into the water block for better cooling. So with that, I will move on to Killian here, and he will talk about liquid cooling.
Hello again, my name is Killian Davis. I'm going to be talking about liquid cooling. Liquid cooling is defined by the process of phase changes, evaporation and condensation. As a liquid evaporates, it draws heat, and then vice versa. As a gas condenses, it gives off heat. And this is also brought on by high and low pressure. As you apply high pressure to a gas, it's going to condense, and then as a high pressure liquid reaches a low pressure system, it's going to evaporate. So if we're looking at this system right here, the components to notice are a compressor, condenser coils, evaporator coils, and capillary tube. If you have a high pressure liquid right here, because it's in a small diameter tube, it'll reach a low pressure system inside the freezer, refrigerator, or whatever you're working with. When it reaches this low pressure system, it expands because it's been under such high pressure. As it expands, it evaporates and draws heat. The gas is then fed into a compressor where it's placed under high pressure, and then it is compressed into a liquid again where it will give off heat and condenser coils, and then the process recycles. The liquid that is used in this process is generally Freon. They're trying to stray from it because of its ozone hazardous materials, but it's used because it has a high specific heat capacity and it very simply transitions between states. There's a couple different compressor types that all the applications work with. There's high temp, medium temp, and low temp, and they mean exactly as they're stated. High temp compressors are generally worked with very high ambient temperatures. So we're looking at HVAC systems in automotive vehicles and then air conditioning units. Automotive vehicles' engine blasts can generally get up to near 200 degrees when the engine's running, so you don't want your compressor to burn out over time, so manufacturers want to make sure that they can handle that type of heat range. Same with AC systems. You're generally not working as in high temperatures in an HVAC system, but they can be working in outdoor conditions because AC units are generally placed outside. So the compressors can be getting sunlight directly on them in areas such as like Phoenix that can get above 100-degree temperatures in the summer. The next type are refrigerators, and refrigerators are medium temperature because they're generally sitting in room temperature areas like kitchens that are going to be about 70 degrees plus. They can generally reach up to about 110 degrees Fahrenheit ambient. I got that number from GE's manufacturing company. But anything above that, the efficiency generally goes down and the compressor will eventually just burn out and die. Low temperature compressors are generally chest freezers. They will regularly not be put above 75 degrees because it's cooling to such a low range. Generally, freezers are going much below freezing to make sure food is consistently kept frozen. So if you're putting it in areas above 75 to 80 degrees, it's just not going to function at all and your food's not going to remain frozen. So I want to quickly just summarize some of the applications of it, which you all are aware of. But one thing to notice about a compressor in general is that compressors require a very high startup surge current. For everyone who's taken 320, which should be everybody in here, we know that torque is required for an engine to start, or a motor. And torque directly correlates to current. So generally for every compressor, 3 times the running current is required to start the motor. So we see this with energy bills and everything else. So when we're looking at HVAC systems, we see that they're a very high current draw. So if a car is sitting in a parking lot all day in the beating sun, it can reach up to about 103 degrees temperature inside the car. So auto companies want to make sure that the driver is going to be comfortable. So they want the system to cool very quickly. In order to do that, it has to draw a very large amount of current to make sure the phase changes occur very rapidly, so it works at a very efficient rate. So if you're driving down the freeway and you have your AC on, you know your fuel economy is going down because you're drawing so much power. Same thing with an air conditioning system. One thing to notice about air conditioning systems is that they're measured in BTUs, which are British thermal units. These directly correlate with power and energy generated by our room. As the BTU number increases, so does the current required by the compressor, and thus the cost. So as your current increases, then so is the bill you're going to be paying at the end of the month. So the higher the BTU value, the more money you're going to be paying. The next types are refrigerators and chest freezers. refrigerators generally have a very low current pull, and that's because a refrigerator is generally in a room temperature area. And you're not going to be cooling your fridge below freezing. You're generally going to be cooling it to about 37 to 40 degrees. When you do that, that's a very low temperature range that it has to drop. So you're only going to be pulling about 1.5 to about 4 amps. And that's running current, not completely starting. And then the next type, chest freezers, have a very high cooling requirement because you're sitting in an ambient room, but you have to cool much farther below ambient, which is going to be below freezing, which is going to require generally about 4 to 7 amps running current, and that also multiplied by 3 to start up for regular. And after that, I'm going to hand over to Mike to talk about Peltier devices.
Morning, class. My name is Mike Rebell, and I'm going to go over Peltier effect, or otherwise known as thermoelectric cooling. So we'll start off with the history of the Peltier effect. Though it's used today, it's actually a relatively old term. It was founded by a French physicist named Jean-Charles Peltier in 1834. And he discovered once you combine two junctions of two different types of metals and apply a current through the metals, it creates either a cooling or heating device dependent on the path or the direction of the current. Some of the key components of a Peltier device are the current obviously being applied to the device, the semiconductors, the ceramic plates that hold the device together, and also the metal conductors that combine the whole circuitry together. Some of the applications for Peltier device, mostly they're used on microcontrollers and other computer architecture. They've been known to be used in cars for coolants for cup holders. So now we're going to look at the guts of a Peltier device. Starting off, we'll talk about the P-type and N-type semiconductors, as you can see these squares here. Depending on the size, the dimensions, and the type of material of the P-type and N-type semiconductors, that all add up to the heat absorption rate, or how much the device cools. Moving on, we'll look at the metal conductors, which essentially connect all the semiconductors together. These are placed at the top and bottoms of the semiconductors and create an array of cooling that combines all the semiconductors for cooling capacity. Next, we'll take a look at the ceramic plates. These are essentially what either heat up or cool, or either heat up or get rid of, or cool down whatever you're trying to cool. They're placed at the top and bottom of the device, and they bring everything together and insulate. And then we have our current source. Depending on how much power, the more power you use to your Peltier device, the more it cools, but it comes at power inefficiency. Now we're going to talk about the actual Peltier effect and how it works. So the semiconductors are paired up, and then they're connected by an array by the metal conductors. So when current is applied through, electrons are being forced across the metal conductor from P-type and the N-type. The P-type is at a lower energy state, and it's moving to a higher energy state. In order to make that jump from Fermi levels, from a low to a high, you have to grab energy somehow. This is when energy is absorbed from the environment, and heat is absorbed and the ceramic plate gets cold. When you go from N-type, and then this metal conductor will be connected in an array to the next P-type, you're going from a high state into a low state. When that happens, you're losing energy, otherwise known as giving off heat. Here's some key variables for determining how effective your Peltier device is. As mentioned, the heat absorption rate is what you're trying to obtain. The more conduction current you apply, the higher your heat absorption rate is, but it becomes inefficient when you apply more current. Two other key factors are the temperature of the heat dissipating surface and the temperature of the heat absorbing surface. Now, for optimal cooling, you want both of these surfaces to be the same temperature. As they start to vary, that's when you start to get efficient with your device. The number of semiconductors is very important. The larger your Peltier device is, the more semiconductors it has, meaning the better it cools, but once again, it becomes more efficient. Now, bringing all those components together, you have your cooling and your heating. The only problem with a Peltier device, as mentioned several times, is for every 0.5 joule of cooling is achieved for 1 joule of electricity used. So if I had 50 or 100 watts being applied power to the device, and typically only about 50 watts will be absorbed, then you have to somehow figure out how to dissipate 150 watts from the device. Pros and cons. There's no, unlike AC units, there's no cryogens needed, such as Freon. It's very small, solid state, there's no moving parts, so that leads to longer lifetime. It's stackable, so if you wanted to, for whatever surface you're cooling, you can put 2 devices on top of each other that'll essentially improve the cooling. There's no maintenance cost because you got temperature, precision temperature control. You can pretty much buy any type of wattage that you wish to dissipate for online. And then some of the cons are direct contact needed. It's not really used for ambient cooling air. As mentioned, it's highly inefficient, very expensive, and it has large power requirements.
Hi everyone, again my name is Colin Underwood. In conclusion, we went over 4 cooling techniques here. Air cooling and heat sinks, which was given by Cerrone, was the heat exchange through an increased surface area of a metal, usually achieved through the use of fins. This can be either active or passive cooling. Second, we gave a presentation on water cooling. This was given by Mason. This is the use of radiators through a closed water loop system, which allowed for the cooling of multiple electronic components. You use the heat capacity and the specific heat of water to achieve this cooling. Liquid cooling, which was given by Killian, was the use of a compressor to invoke a pressure-induced phase change of a liquid, in this instance Freon, to promote heat exchange within an airtight system. And finally, the Peltier cooling module was given by Mike. This was the use of N-type and P-type semiconductors and a determined direction current flow to achieve cooling. There are references, and thank you for your time. Are there any questions?
Any questions from the class? Anybody? All right.
John?
Which one do you find to be most effective concerning your project?
Liquid cooling was the one that we're using. In our proposal presentation, we said we were going to use a refrigerator. Upon further research, we found that the compressors in a refrigerator, like I stated, were only go up to about 110 degrees Fahrenheit, maybe, and that was what I got from GE for just small refrigeration units. And so we switched to actually an AC unit instead that we're going to utilize. I'm sorry. Switched to an AC unit that we're going to utilize instead because AC units can handle up to about 200 degrees. So liquid cooling is airtight as well, which is the important fact there, and it can cool below ambient temperatures. And we're going to have ambient temperatures where we are about 130 degrees, which is what our design project is.
Okay. Any more questions? Thank you.